In this fourth lecture on advanced quantum mechanics, today we shall discuss the generalized angular momentum in momentum operator and its study in quantum mechanics. Earlier, we have solved the orbital angular momentum problem in quantum mechanics. Firstly, we started the problem started the problem from classical expression that L orbital angular momentum is r cross p, and then using Bose correspondence principle we obtained the operators corresponding to this, and in position basis r operator is r itself and p operator p vector operator is minus ih cross nabla. Using this we solve the differential equation and obtain the eigenvalues and eigenfunctions for the simultaneous wave function, simultaneous eigenvalues, simultaneous eigenfunctions of L square and Lz operator. We solved the problem yet another way in which we utilized only the commutator relation amongst the Cartesian components of orbital angular momentums. In our relativistic quantum theory, we have seen that in the orbital angular momentum is no more a constant of motion. Rather, we require to define the J operator, which is the orbital L plus S, where L is the orbital angular momentum quantum, orbital angular momentum operator, and S is the spin angular momentum operator, and J is called the total angular momentum, and in quantum mechanics they are operators. The Schrödinger prescription is not applicable to S or J because neither S nor J has any classical analog. So we cannot start with from a classical expression and then quantize it. There is no provision. So if we want to study the angular momentum in general, first of all we are to redefine angular momentum which is applicable, and that definition should be applicable to L, S as well as J. So we are after a generalization of the definition of the angular momentum. Now we know that the components of L, the Cartesian components of L operator satisfy this commutator relation IH cross summation over gamma epsilon alpha beta gamma L gamma, where this is the Levy beta tensor, and it is 1 2 3 is equal to epsilon 3 1 2 is equal to epsilon 2 3 1 is equal to plus 1, epsilon 1 3 2, epsilon 2 1 3, epsilon 3 2 1 is equal to minus 1, and other 21 values having repeated index are 0. So that is to say that Lx Ly is equal to IH cross Lz, and Ly Lx is equal to minus IH cross Lz, etc. If we write it explicitly for xy component, so Lx Ly commutator, which is Lx Ly minus Ly Lx, this is nothing but the L cross L operator. If we take the Z component of it is this, and this is equal to IH cross LZ operator. So in that sense we can write this commutator relation in an alternative way. L operator cross L operator is equal to IH cross L operator. You recall that in matrix mechanics we started with this commutator relation. So in Heisenberg formalism of angular momentum, this relation is sufficient to form to find out the eigenvalues and eigenvector of the orbital angular momentum operator. So we define generalized angular momentum to be one which satisfies this relation or equivalently this relation. Any set of three quantities whose Cartesian components satisfy this equation or equivalently this equation is termed as an angular momentum operator in quantum mechanics. So we see that for spin the relation is S alpha S beta is equal to RH cross epsilon alpha beta gamma S gamma, where there is a repeated index of gamma, so the summation over gamma is implied. And for J it is J alpha J beta is equal to IH cross epsilon alpha beta gamma J gamma. Alternatively, we can write S vector operator cross S vector operator is equal to IH cross S operator, and for this J vector operator crossed with J vector operator is equal to IH cross J vector operator. Exactly same definition. So this is the generalized definition. Starting from this definition, we shall work out the quantum algebra corresponding to J, and which is the total angular momentum. You need to know that J is equal to vector L plus S. If we put S is equal to 0, then J becomes L. If we put L is equal to 0, then we get J is equal to S, and when both L and S are there, we get the total angular momentum. So the theory that we are going to develop with J is equally applicable for L and S. For L we have to set S is equal to 0, and for S we have to set L is equal to 0. So our starting point is this commutator relation. Jx Jy is equal to IH cross Jz, Jy Jz, Jy Jz is equal to IH cross Jx, and Jz Jx is equal to IH cross Jy. These are the three basic commutator relation. We define J square operator as equal to Jx operator plus Jx square operator, Jy square operator, Jz square operator, and it is a trivial task to show that J square operator commutes with each of its Cartesian components. So we can look for simultaneous eigenvalues of J square and any one of its Cartesian component. Due to historical reason, we look for simultaneous eigenvalue of J square and Jz, and we set this as let J square is equal to lambda H line square. We are using Dirac's notation, Dirac's bracket notation. That is to say, we assume that j square lambda alpha to be the simultaneous eigenfunction of j square and jz. For j square, the eigenvalue is lambda h line square, and for jz it is alpha h line. We know that h line is the natural unit of angular momentum, so lambda and alpha are dimensionless quantities. Now the next step is to define the ladder operator. J operator plus minus is equal to jx plus minus I jy, and the commutator relation of jz with j plus. This commutator relation is jz jx plus I jz jy. This part is IH cross JY, IH cross JY. This is IH cross JY, and this is minus IH cross JX. So we get IH cross JY and plus I times minus IH cross JX. So this is minus I square, which is I. So taking H cross common, this is JX plus I JY, which is plus H cross J plus. Similarly, we can show that JZ commuted JZ with J minus is equal to minus H cross J minus. So this commutator relation will be required in afterwards, so we note them. JZ J plus minus is equal to plus minus H cross J plus minus. And obviously J plus minus is well known. It is Jx plus minus I Jy. Now we want to show what is the action of J plus minus when it operates on the lambda alpha lambda bucket. So we start with Jz J plus. This operates on lambda alpha, and on the right hand side we have plus H cross J plus lambda alpha. If we unfold the left hand side, we get Jz J plus operating on lambda alpha, then minus J plus and on the right hand side we have plus H line J plus operating on lambda alpha. This part, as per this assumption or definition, which is alpha H cross lambda alpha, so this quantity altogether is lambda alpha H cross going out J plus lambda alpha. So we take this quantity on the other side and we rewrite this equation as Jz operating on j plus lambda alpha. This is the left hand side, this side part is taken on the other side. So this is alpha h cross, and when it is taken to other side it is plus. So h cross alpha plus 1 j plus lambda alpha. If we compare this equation with this, we see that when j plus operates on lambda alpha, it produces a state whose alpha value is increased by 1. That is to say, j plus operating on lambda alpha gives you a state c plus with a constant times the lambda value remains the same, alpha value is increased by 1. So this is the raising operator. Similarly, we see that j minus when operates on with the lambda alpha value is decreased by 1. Our aim is to find out the constant c plus minus. To this end, we recall that the Hermitian conjugate of j plus is j minus. No, j plus Hermitian conjugate is equal to j minus plus. They are the Hermitian, one is the Hermitian conjugate of the other, and we consider the quantity j minus into j plus. This is jx minus ijy times jx plus ijy. If we multiply this with this, this is jx square operator, this with this is plus jy square operator, and this multiplied by this I plus I jx jy, and this is, and when this is multiplied with this with minus jy jx, note the ordering does matters. This part can be written as j square operator minus jz operator square, because j square is jx square, jy square, jz was missing, so jz added over here and is subtracted, and this is commutator of jx jy, so this is plus I times ih cross jz. So this is j square operator minus jz square operator by minus h cross jz operator. If we use the minus for plus first and minus, then this would be j square minus jz square plus h cross jz. So these two relations will be of use. J minus j plus is equal to j square minus jz square minus plus minus h line jz and j plus j minus is equal to j square minus jz square plus h cross jz. We consider this expression j plus operating on lambda alpha is C plus lambda alpha plus 1. We take the Hermitian conjugate of it, so this is lambda alpha, this is j plus dagger, so j plus dagger is simply j minus, as we have written over there. So this is j minus, and this is this side, and this is C plus star lambda. If we take the inner product of these two relations, we get lambda alpha j minus j plus lambda alpha, and on the other hand side C plus this is 1, or C plus modulus square is equal to this thing, and we write L minus L plus, this is J square operator minus JZ square operator minus plus. So this is minus H line JZ operator operating on lambda alpha. You see that the result is lambda alpha, j square operating on this gives you lambda h line square, jz square operating on this gives you alpha square h line square, and jz again operating on this gives you h line square alpha lambda alpha. So this is h line square lambda square minus alpha square minus alpha. So we going similarly, we get C minus square would be h line square lambda minus alpha square plus alpha. So C plus minus is equal to lambda minus alpha square minus plus alpha. So far we have found that alpha value, that is the eigenvalue of LJZ operator changes by unity. That much we have obtained. Still we haven't found any relation with lambda and alpha. To this end, we say that for a given value, let for a given lambda alpha max and alpha mean are the extreme values of alpha. Now we consider the state lambda alpha max. This state. This is the maximum value of alpha. If we further operate it by j plus, it should be a null ket, implying that lambda minus alpha max square minus alpha max is equal to 0, or lambda is equal to alpha max square plus alpha max. Similarly, consider the ket lambda alpha mean. This is the lowest value of alpha. If we operate this by j minus, we get again a null ket, which gives you lambda minus alpha mean square plus alpha mean is equal to 0, or lambda is equal to alpha mean square minus alpha mean. If we equate the lambda, two lambda values, we get alpha max square plus alpha max is equal to alpha mean square minus alpha mean, or alpha max square minus alpha mean square plus alpha max plus alpha mean is equal to 0. If we factorize this, we get alpha max plus alpha mean, and then alpha max minus alpha mean plus 1 is equal to 0. The alternative is alpha mean is equal to minus alpha max, and or alpha mean is equal to alpha max plus 1. So alpha mean is greater than alpha max, so this cannot be the possible way, because as for our assumption alpha mean is the minimum value, so this is the right choice of it. So if we call this value to be minus j, we call it minus j, say this is minus j, then from this relation we get the lambda value is equal to j into j plus 1, and this value is minus j square minus or minus j again j into j plus 1. So we say that lambda value can be written as j into j plus 1, and for a given lambda alpha ranges from minus j to plus j in unit step. And we call this mj alpha as mj, and we redefine the ket lambda alpha to be j mj. So we see that we get a relation between j eigenvalues of j square operator and eigenvalues of j square operator. So let me first rewrite the eigenvalue equation. Eigenvalue equation comes out to be j square operating on j mj is j into j plus 1 h line square jm, and jz operating on jmj is equal to mj h cross jm. So these two relation has been redefined or reformulated. Now we are to write these two relations. Now coming to j plus operating on jmj. This is h line square. You see it is lambda, that is j into j plus 1 minus alpha square, this is mj square, and for plus it is minus mj, and this is j mj plus 1. This is j square minus m, this can be written as j square minus this quantity within square root can be written as j square minus mj square plus j minus mj. This is j minus mj taken common, then this is j plus mj plus 1. So this we write as h line j minus mj and the other one is j minus j and j is equal to h cross. This becomes j into j plus 1 minus mj square plus mj under root. Then this is j mj minus 1. This is equal to h cross. J plus mj, j minus mj plus 1 if we stick to this representation. This is the representation in terms of the quantum numbers of the eigenvalues or quantum numbers for j square and jz operator. So in this notation we can find out the matrix elements for other quantities. As for example, if we consider the matrix element j prime mj prime j square operator j mj, this is j into j plus 1 h line square times delta jj prime delta mj prime, because when this operates on this we get j into j plus 1 h line square j mj. This is being scalar, is taken out, so and when it is its inner product is taken with this bar, we get j into j plus 1 h line square taken out, then j prime j mj, which is equal to j into j plus 1 h cross delta jj prime delta mj prime. This is the matrix element. So that is to say only the diagonal elements will be there. Similarly, j prime mj prime jz j mj is equal to mj h cross delta jj prime delta mj prime. Now we come to the matrices for L plus and L minus. We know that J plus operating on JMJ gives us, keep a space, this is H cross under root J minus MJ into J plus MJ plus 1. We are using this relation, J MJ plus 1 ket. When we take the inner product with the J prime MJ prime, we get so the result is, taking the scalar part out, J prime delta mj plus 1 mj prime. You see finally the dot product is j prime mj prime with j mj plus 1. So jj prime delta function is jj prime and mj prime with mj plus 1. Similarly, the matrix element for j prime mj prime, j minus jmj is, I'm writing the final step only, h cross j plus mj, j minus mj plus 1, then delta jj prime delta mj minus 1 mj prime. And if we want to find out the matrix for j, first thing we see that this matrix for a given value of j, mj has values from minus j to plus j in steps of unity. That is, for a given value of j, mj has 2j plus 1 values, and these matrices are not diagonal. If we consider a particular value of j, these two matrices, there is a matrix for j square and jj are diagonal, but for j plus and j minus, the diagonal elements are 0. If we are to find out the matrix element for jx, we recall that jx can be written as half j plus j minus. So from j matrix element of jx, j plus and j minus, we can find out the matrix for jx. Similarly, jy is minus I by 2 j plus minus j minus. So we can get the values for jx and j matrices for jx and jy from the matrix of j plus and j minus. In the next class, we shall find out the explicit matrices for these operators using first three possible values of j, that is j is equal to 0, j is equal to half, and j is equal to 1.